So today I'm going to go into more detail about HTTP, which is an important application layer protocol, which I kind of touched on last week. And this will be enough information to get you started with the project, if you haven't already. Okay, so first of all, announcements. Don't forget that there's reading to do. I'm not going to always tell you what chapter we're on. I mean, I should, but sometimes I'll forget, like I did already, and someone came up and asked me, and I just put the bullet in before this lecture started. All right, so chapter 2 is what we're covering right now, and then I'll go to the next lecture. Do keep up. It'll help you a lot. Homework 1 is due on Thursday next, and project 1 is due on Tuesday next. And the project is going to take you a significant amount of time, so please get started as soon as you can. And the sooner you start, the better off you'll be, not just because you'll have more time, but because you'll be able to go to lab hours. So today we had our first on Monday, 10 o'clock to noon. And Tuesday we have lab hours after classes in the Wilkinson lab. And Friday, Caillou has lab hours from 4 to 6. So take advantage of that if you need help, especially with like the programming part of the assignment, right?
What happens during lab hours? Is it just like
it's like office. It's TA hours, yeah. The reason I call it lab hours is because it's in a computer lab where you can go and sit down and work. Even if you don't have a question immediately, you can just start working. Okay. And then as things come up, you can go and talk to the TA, right? There's plenty of space for you to do that. So that's a little bit different than traditional office hours. Yeah. Okay. And I suggest that you actually, so even though the homework is due after the project, 2 days after, I suggest that you definitely start the homework first, do parts A and C, which are Wireshark labs, because those will definitely help you understand what the project is talking about. All right? All the sort of like little mini essay questions or short answer questions in the homework, you can wait to do those until later. But in getting experience with Wireshark and looking at HTTP in the homework will help you with the project. All right? Any questions about that? Okay. So last lecture, we talked about like the network. We talked more about chapter 1 material, which is a summary of the whole course in a little more detail. Talked about circuit switching versus packet switching. The internet uses packets. Packets travel along many hops to reach their destination, and every hop has a delay that comes from 4 different sources. There's delay in the node itself from processing and queuing. There's delay in the link due to transmission and propagation, which are slightly different things. Along the hops that the packet travels to reach its destination, there's a possibility, routers are the devices that handle the packets at those hops, and it's possible that a router might be full. In other words, it has no space and it's queued to store the packet might be dropped for that reason. That's one reason that the internet is unreliable. Another reason is that the link may have some corruption, may introduce some corruption in the packet, and therefore the router may see that data corruption and drop the packet for that reason, not because it's out of space or because it sees the data error in the packet. I talked a little bit about the sort of high-level architecture of the internet, that it's a network of networks. You have tier 1 ISPs and big content providers that have these high-speed backbone links, and they peer with each other to connect each other up and create this global interconnected network. And then the kind of like smaller ISPs are the ones that little customers deal with to buy service from, buy connections from. Internet uses, and networks in general, use layered protocols. In particular, we have like Ethernet at the lowest level, then IP on top of that, TCP, TLS, HTTP. We're going to talk about all these things in detail in different chapters of the book. And we're starting with HTTP and working our way down to the lower level. A socket is a software abstraction of a network connection. In the first project, you're going to use sockets, and also in the second project. And you can think of it as a TCP socket. You can think of it as one end of a pipe that you can send data into. You can send data in, get data out, streams of bytes. And each socket is bound. Of course, it exists between your machine and some remote machines. There are 2 different machine addresses involved. There also are port numbers assigned so that you can have different sockets living simultaneously or operating simultaneously on one machine. In other words, the ports give you like addresses within a machine to distinguish between different connections and different software that's using the network. And like I said, I started talking about HTTP which is an application layer protocol. And today I'm going to go into a lot more detail about that so that you really know what to do with the first project. That shouldn't have spun. Sorry about that. So I introduced layering before, and this is a reminder that when we have a data packet that's sent on the internet, it has a lot of header information that's associated with different layers of the system, and then at the very bottom, at the end of the packet, you have the actual data that you're transferring, the application is transferring. In this case, I'm showing HTML document, and then there's data associated. There's a header associated with the HTTP application layer. There might be a header associated with TLS encryption and authentication. Above that, there might be a header associated with TCP, which handles like ordering the packets and reconstructing the packets. We'll talk more about the details of all this stuff later, but I want to just present this high-level picture again. And then higher up, we have the IP header, which gives the information that the packet needs in order to get it to its final destination across many hops. And then at the Ethernet is the very beginning of the packet that has information that allows the packet to get across the first hop that it's the hop that's immediately the link that's on. One hop. All right, we'll talk more about that stuff later. So what is an application layer protocol? This is a protocol that is used to build software applications. Okay, you might guess, but what does that mean? So the purpose is to allow applications running on different computers to communicate. So here we have 3 different computers that are, they want to talk to each other, and all they know about each other is maybe some address, which is maybe an IP address or a host name. We'll talk more about what those things are later. But for this computer, all it knows is that there's some software running, and that software wants to talk to some other computer and send some data. And an application layer protocol does that, or that's what an application layer protocol is. So there are 2 general categories of application layer protocols: client-server or peer-to-peer. And we distinguish between those 2 based on whether or not this protocol relies on a centralized server. If it does, then it's a client-server protocol. You have many machines that generally talk to one centralized location, and that centralized server then distributes data back out to the appropriate client. And when we're working at the application layer, the important thing to remember here is that we don't have to worry about the low-level details of the network. There are a lot of details that we're eventually going to understand. Things, how we break up the data into multiple packets, how we make sure those packets get across all the hops, how an optimal path is used to get to its final destination. We're not worrying about that stuff yet. We're assuming all that is going to be worked out. We're assuming that we can create a socket that connects somehow to some remote location. You're going to do that in your project. You'll see how easy it is because the operating system and the routers and the network handle all the low-level details below the application layer. So we assume that we can send messages of arbitrary size to another host on the network just by specifying the IP address of the remote location or the DNS host name. So the client-server architectures, like I said, have clients and then servers, or like maybe one server in the simplest case. And in that case, so what's the difference between a client and a server? It's a pretty simple concept, I guess. But the servers are there to serve clients, so hence the name. They handle requests. So basically, the servers are always listening. They're always on. They have permanent IP addresses or DNS names, so that the clients know where to reach them. They're usually in a data center that has reliable power and cooling and all that stuff. And they don't have a keyboard or mouse. No one's using the server to browse the web or something. They just are running software that handles requests from clients. Okay. And clients are what you're most familiar with. Those are laptops and smartphones that runs various software that makes requests to servers. Right. So clients are the opposite of servers in every way. They're not always powered on. Their IP addresses change. They're not in data centers. They do have displays and keyboards and mice. And they cannot listen to requests from other machines generally because might be some firewall in front of them. Or like I said, they have a different IP address all the time. So it's infeasible for them to listen to requests. Yeah.
Could you explain more about the no display keyboard or mouse?
Yeah. So basically, what I mean is that in a data center, you have racks of computers that are just plugged into power and network, and that they don't have keyboards and mice. And if you want, maybe when the machine was first set up, when the operating system was installed, some technician may have plugged in a keyboard and mouse temporarily, maybe plugged in a CD drive or something to set it up. But then the software is set up so that you can turn it on, and it'll boot up, and it'll automatically start the necessary programs that the machine is intended to run, like a web server or a mail server. And then most of the time, like I said, there's no keyboard, no mouse. In order to make any changes on that server, to monitor it, to turn it off, reboot it, you have to SSH into it. You have to use some kind of network remote access system protocol to log in and get a virtual terminal, right? Okay. So peer-to-peer architectures are different than client-server. They're less common, but in this type of a system, you don't have servers that are different than clients. You have all the machines are kind of equals. They're all peers, meaning equal, and they all have the responsibility for listening to requests from other machines, and so they basically the work that typically is handled by a server is distributed among the machines that are using the application. This is a scalable design because in a client-server system, like let's say you're running Gmail or Yahoo Mail or something, if you have 1,000 customers, you might only need one server to handle that traffic and store the messages. But if suddenly you have 100 million users, you would need maybe hundreds of servers to handle that. And so it gets expensive you have to keep adding more machines, and that might get expensive. And if you don't add more machines, it'll slow down and stop working. A peer-to-peer architecture, whenever a new customer or whenever a new peer comes online to use the service, they are using the service, but also they're providing computing capability to everyone else in the system. Okay. So that's what I mean by saying that it's scalable. There are not too many systems that use this design. BitTorrent is one, Skype is another. Because it's difficult to design this kind of a system, for all the reasons that, because of the characteristics of clients, the fact that, like I showed before, they move around, they're not always on, they have different IP addresses at different times of the day or the week or whatever. So it's difficult to find somehow the location of all these machines and the responsibilities of all the different machines has to be managed in a distributed way. And that's a challenge. And this is a whole big topic of research and of activity in industry. So we have a class on distributed systems that covers this to a degree. Anyway. And the simple mail protocol, the SMTP, simple mail transfer protocol, is actually kind of an example of a peer-to-peer architecture because you have many different mail servers that handle the email from different domains, like Northwestern.edu has a mail server. Gmail has its mail servers, and so on and so forth. All those different mail servers send mail to each other depending on who the recipient of the mail message is, right? But that's not; those are still kind of servers in some sense because they're, they're always on and they're data centers and whatnot. Okay, so I want to give a little history of peer-to-peer. Before we move on, this is probably the last we're going to talk about peer-to-peer architectures, unfortunately, in the class because it's more of an advanced topic. But Napster, I think, came online in 1999, and this was like a very innovative application. This was the first true peer-to-peer application on the internet, and the problem it solved was giving people free music illegally, right? So basically, it allowed people, usually on college campuses, to share the files that they had on their own computer, MP3 files. MP3 was a new thing at the time, and others could look up files they wanted to find, and you could see at any given time, like this, at this time there are 9,700 users online, and they're sharing, 1.7 million files, 7 terabytes of files. So this allowed someone who wrote a software application like this without having any servers or infrastructure, with very little cost, allowed this kind of global network of this application that handled a lot of data to operate. Of course, it was shut down after copyright lawsuits, but this design was kind of very innovative and inspired BitTorrent, which also is not necessarily always used for legal purposes, but it is also a very technically interesting and useful, for legitimate reasons, protocol. So I wanted to ask, why do you think it was important for Napster to use a peer-to-peer architecture in its design? Yeah, over there.
I guess it's kind of hard to shut down by like legal entities.
Yeah, so it's harder for someone to shut you down because basically, once you give the software to people, they're all communicating to each other. So to shut it down, you have to kind of go around to all the individual people running the software. I mean, it turns out that actually they could shut it down because it wasn't purely peer-to-peer. There was some centralized aspect of it. Like there was a centralized directory server that would be the first place that the software would go to find out about other people nearby. And like newer systems and research systems avoid that centralized aspect, but that is definitely part of it. Other suggestions? Yeah.
Because each like host can be a server, can also be a client.
Well, that's the definition, but why is that good?
Like people can share things they have, so there not be like a congestion when they like requests from server.
Yeah, so there doesn't have to be a server that handles all of the data. It's scalable, right? Users can start sharing their data immediately without first uploading it somewhere, because then it'll just be pulled on demand from the various clients.
Also, then there was like decentralized storage, so you don't have to keep that many.
Yeah, you don't have to have big storage somewhere centrally. Yeah, any other ideas?
You also don't need like one organization to buy all the rights to the music. You have it coming in from everyone.
Well, yeah, it's illegal file sharing, so yeah, there's that.
Is it because also like IPs can always change for each of the peers, so it's really hard to track down like one IP if the person's floating around?
Yeah, so for an illegal music sharing service, it's difficult for the users to be accountable because they have a certain degree of anonymity and mobility. Their IP addresses change. So this allowed. I mean, I think that the students who were using this were mostly naive and weren't thinking too much about whether or not they were going to get in trouble for using it, just because it provided a good service. But I think also there's some truth in thinking that the people using this could to a large degree not expect to be punished because they were kind of anonymous on the internet. Yeah. All right. So that was that, and it shut down. But it's an interesting protocol and was influential. Okay, so coming back to client-server architectures, HTTP stands for Hypertext Transport Protocol. Hypertext is like HTML. Also stands for Hypertext Markup Language. Text with links, basically. Right, so it's a client-server data exchange protocol. It's built on top of TCP, like I mentioned, and it was invented for web browsers to fetch data from web servers, right, to support the web. And it sort of involves transactions that are requests and responses, which is generally what the most common form of network communication. It's not the only kind. Sometimes on networks you just broadcast data without necessarily expecting a response. But HTTP has a request and a response, right? In the request, you have a human-readable header. One important thing about HTTP, and you'll see this in the project and Wireshark, that it's all human-readable. Like if you look at the bytes, they're ASCII characters that form English words that you can read through, which is convenient. It means it's kind of loaded. It's kind of large. It wastes space compared to what you could optimally do, but it makes it a little easier to debug and design. There's a header that has several things, but it always has a URL and a method, like get, post, put, something like that. We'll talk about those later. There could be a body in the request, especially if you're kind of uploading data, if you're posting data. And then a response comes back that has, again, human-readable information in the header, including a response code, basically indicating whether the request was successful or failed, or some in-between cases. And then there's a body usually or optionally, that has the data you requested. Usually, or if you provided data, there might be no body, because it's just acknowledging that the data was received. Okay. Okay, so here's an example of an HTTP request. So it's all in plain text. That's what I mean by it's human readable. So if you were to decode the bytes in the packets, they would each, like the first byte would be whatever number corresponds to G in ASCII. And so you get this translation into ASCII. The first line is called the request line. It has the method here, some kind of verb, and then the URL that you're getting. And the stuff after that are headers. And some of these are optional, some are required in certain cases. But this gives you, more information about the request. And then there's a blank line. And once you see a blank line, you know that what follows is the body of the request, if there is one. Okay. And then in response to that, in this example, you have the first line is a status line that indicates the response code. 200 OK is the response. So 200 means OK. There's a number for the response code. There's also a little phrase that goes along with it. There's some more headers. Like for example, the date is included on this one. There's like a hash of the data in case you want to cache it. And there's content length, which tells you how much data is down here. This connection closed tells the client that we should close this TCP connection after this. We're not going to use it again. And then again, there's a blank line that signifies that the following data is the body. And you can tell how much data to read down here based on what you read in the content length.
For the request headers, is the order always in that kind of structure? Will host always be above next step?
No, the order is irrelevant. The first line has to be the request or the status, but then these headers can be in any order. And you could ask about corner cases, can things be repeated? What happens if you say content length 35 and then content length 40? That's nonsense, but how your program deals with it, if you're writing a HTTP program, you might want to figure out what to do in that case. And if you have these questions about the details of the protocol, you should read the RFC that describes the specification for HTTP. Okay, so I wouldn't know offhand. Personally, what should happen if a header is repeated. And sometimes weird corner cases are not don't have defined behavior based on the protocol, and you should avoid those cases. Okay, so just going through this in detail, the way that this HTTP transaction I just showed you happens is first the client creates a TCP socket. So we have a client to talk with the server. This, like I said before, you can think of a TCP socket as a bidirectional pipe or a stream of bytes. You can send data and receive data. So you can create that connection first. We'll talk, later on in the course, we'll talk about what that means and what packets get exchanged and why that step is necessary. But then the client creates an HTTP request. So for example, if this was a browser program, the user typed in a URL into the navigation bar. The software would then know that it has to send out a request to get the data, the page associated with it. So it constructs a request and starts writing that request to the socket. The server notices that there's new data coming in on the socket eventually. And it starts reading. And eventually it notices that it's received a full HTTP packet. So it might start reading, it might read one chunk in one call, then read another chunk in another call, and so on. And you'll have to, in your project, you'll see how that works. You don't necessarily get it all at once. But eventually you notice it's a full request, and now it's the server's turn to do something. So the server reads the request, based on what it knows about HTTP, it interprets it, and it generates some response. Okay, that's down here. In this case, it's an OK message with some HTML down here and some metadata. Yeah?
So does the server know that it's getting an HTTP request just based off the first line, or does it wait until it gets everything to figure out what it is?
How the server knows that it should interpret the message as HTTP is usually based on the port number that was used. So this TCP connection was established by the client to connect to a certain server on port 80. That's the default HTTP port. And this server happens to be running software, web server software, that listens on port 80 because all it does is handles HTTP requests. So based on the fact that the client specified because the user typed in a valid website into the browser, that website corresponds to a machine that is running a web server that's listening on port 80, and it's expecting HTTP. Yeah.
On that point, is there like a dedicated like port or socket on like the server side for each client connection?
So you'll see how this works in the project. There is a dedicated listen socket that listens for new connections on port 80. There's one of those. But every time a new client makes a connection to port 80, it creates a new socket to handle that transaction. So there can be multiple clients connected at the same time to port 80 on the server. Okay, so the server generates a response. It knew it was HTTP because that software is listening to port 80 and it's designed to handle HTTP. It starts writing that to the same socket, but on the output side instead of the input side. And the client gets it, and just like before, the client keeps reading until it kind of notices it has received a full response, and then the client uses that data. And if it was a browser, it would look at the HTML and then call its down parser and basically print that on the screen. Okay. One thing I want to point out here is the way that the two sides know when it's their turn to act. In other words, the way that they notice when the packet is finished, when the message is finished, is by looking at the content length, or by noticing that there's no content length. So in this example, there is a body. So your software can read, when it finds a blank line, it knows that the header is finished. If it had previously seen a content length, then it knows that there are this number of bytes additionally that it has to read. Until it reads that number of bytes, it knows that there's still more data coming in, so it shouldn't start generating a response. And that applies on both sides. Yes?
What if it doesn't say content length? Then
Yeah, so if you read the spec for HTTP, content length is required if there's a body. If there's not a body, then it shouldn't be there. So some requests, like for example, if this was a 404 not found, in that case, there are two ways it could work, but it's possible that there would be no content length and no page, right, because the page was not found. No data down here in the body. So in that case, the client would read this back from the server. It would get to a line, to this blank new line. It would see that, and then it would know that it hadn't seen a content length yet, and therefore it would know that it was done. So if there's no content length, then there's no body. And then you can use the new line here, this blank line, as an indication that the message is finished. Yeah.
And how do you know to keep reading the header? How do you know the new line? But do you just keep reading bytes until you reach a new line? Is that
yeah, until you reach a blank line, there's got to be more header data.
I was about to ask, but if the response code is 404 not found, there still could be problems.
Yes. So
because we sometimes see pages where
exactly, yeah. So if you read the spec for HTTP, like you say, sometimes 404 not found can have HTML. Basically, if you want a pretty page that says not found, GitHub has some animation or some Star Wars themed animation. In that case, there would be a content length and there would be a page, but that's optional. You don't have to have that. So the web browser has to be designed to show some very simple not found message if there's no body. Yes.
This process is already implemented in the socket package in the Python.
What's already implemented in the socket package?
The process that just read the content length and know which to end. Is this?
So Python includes an HTTP library, or maybe several. I don't remember exactly. So because HTTP is so common and many applications use HTTP, Python and many other libraries, Java, have HTTP built in, and it will know how to handle these headers and generate the response code and everything. But for the project, you're actually working at a lower level. You're not allowed to use that library. You have to use sockets, which is a more basic, just TCP level implementation that you get. So in your project 1 code, you have to implement something similar to what's already implemented in Python in some library that you cannot use. Yep. All right. All right, so you saw before some methods and response codes. Here is a longer list. This is not a complete list still, but get and post are the two most common types of requests. So get is for getting data, post is for providing data, basically. Put also puts data, but it's slightly different. Post can get data back, and then there's delete and head. Head is like get, but it doesn't have a body, so it's useful for checking to see whether data has changed. And then response codes, 200 OK is the most common one, but then there are also indications that the content has moved to a different URL. So this is like a redirection. There are two different kinds. 404 not found, forbidden if you don't have permission. And 500 internal server error usually means that the server code crashed. You don't expect to see this, even due to a programming error. And you'll see some of these in the project. And you can read more about them in the RFCs for HTTP. And more of these were added as time went on. HTTP got more popular and complex. And you can also invent your own response codes. Like for example, you could write a web server that returned like a 457 error, and that's not a standard response code. But because it has a 4 at the beginning, the spec says that that should indicate a client error. So the client did something wrong, and you're telling it specifically what it did wrong with some custom response code. Usually 5 means that the server did something wrong. All right, so here's an example that illustrates how this works, how post works with a web page. So here's like an image of a web page that has a login, username, password, and send button. And here's the HTML that implements this, and you'll see that there's this form tag, has method equals post, and action. So this action indicates the URL. And then this stuff here specifies basically these boxes, and it gives the boxes a name. Like the first one's called user, the second one's called password, and then finally there's a button here, and there's a hidden field here as well. So when you hit send, because of, if you look at the documentation for HTML, you'll see it says the rules of that it will cause a certain post request to be generated like so from the browser to a server. So there's a post that goes to this URL bin login, which matches this action, and there's a bunch of data included along with it. So the refer header is like the URL, the page you were on when you did this, and then the body down here has the data that you supplied. The data you supplied includes the values for these two fields and the hidden field that's hard-coded in here. See, user equals Peter Lee. This assumes that you type in Peter Lee here and some password here before you hit send. Action equals login. That's included because of this hidden field. And so this is the body of the request. And this line here, content type, tells the server what format the body is in. And application/x www form URL encoded. This is part of like the HTML standard and HTTP standard for basically the way website forms should encode their data. Yeah. So I'm going to talk briefly about cookies. So cookies are used for web applications to track state, and actually HTTP is a stateless protocol. So the request that you send has to have all the information needed to generate a response. But when one user goes to a web page, like let's say eBay.com or let's say Amazon.com, if I go to that page, I will see product recommendations that are customized for me. So the page I get when I go to Amazon.com is different than the page you get when you go to Amazon.com. So although our browsers are both making similar requests to get the root page of Amazon.com, there's some additional information included in that request that causes the server to generate a different response. And specifically, the different information that our browsers provide are a different cookie down here. So browsers automatically send the cookies back, send a line cookie, and then a combination of key value pairs for for pages that have had a cookie set on them. So an HTTP response that's seen by a browser can have like a set cookie field. So after you, for example, after you log into a website and you're set to, you get the HTML back from the page, from the web server, that web server might also include a set cookie header if it was a login page that you just entered, that you just used or viewed. It would give you some kind of a cookie, some random string, so that later on when you make your next request, the server can recognize that you're the same person who just logged in with a certain username. So the server has a database that's storing this cookie name and mapping that to your username, right? So even though, and if you look at the details of if you look at the developer tools in your browser, you'll see when you visit a page, you can look at the request and see all the headers that are included, and you'll see any cookies that were included in the request. And so usually there are some. Yeah.
So are there rules that govern who can access cookies outside of the server and the client?
Yeah, so the most important rules related to cookies are the browser, if it's going to be secure and keep your internet experience secure, the browser should not send cookies from different pages to different sites. So what I mean is, when you're visiting google.com, it's important that your browser only sends to Google the cookies that are associated with Google, like the cookies that Google knows about. If when I visit google.com, the browser actually sent both my Google cookies and my Amazon cookies, then some employee at Google could see that request and then access my Amazon shopping cart by grabbing that cookie and sticking it on top of their requests that they made to Amazon. So the browser has to, for this all to work, your browser has to be well implemented and like isolate the cookies in different domains. And so when you get this response back that sets a cookie, by default this will be saved only for whatever domain you're currently navigating on. But there can be some details here that specify like a subdomain or some other details about when that cookie should be used and when it should not be used. Yeah.
So like if I view an ad on my Facebook, then I buy it on the Amazon immediately. So in this way, Facebook should not know that I buy that on Amazon.
Well, they probably do know because there are these things called tags, which are little bits of HTML that are placed on these pages that cause your browser to make requests to multiple servers whenever you're doing things that share information to third parties.
Not done by cookie, but.
Well, they are done by cookie. Yeah, that's a good question. I think it would be helpful to have a slide to explain how that works. So maybe next time I'll explain how third-party cookies work.
By the way, like an interesting note of that, I just received an email from Facebook last week that said like to all users who have registered for like Facebook Pixel, that's the plugin, like the script that we put into your page to like track users basically. So they sent like for everyone who were managers of Pixels, they sent a mail saying like we changed how Pixel now works and it stopped being cookie based and we use some new technology. So
yeah,
I have no idea what the like.
Right, I got that email too, but I'm not sure what they switched to and why. Yeah, that's cookies in a nutshell. So get requests so I could actually rewrite that same login page to have a different method specified here instead of post get. This is not actually a great idea, but if I did this, then the form can still provide data to the server by taking that data and sticking it in the URL. So this is like URL encoded data. So it's going to this bin login, which is specified here, and it's got a question mark, and this is called query string. And you have key value pairs here: user Peter, Lee, password, whatever. And I guess the hidden one should also be in there. Sorry, I forgot that. Oh no, it's still there. Action. Let's log in. Yeah. And in this case, there's no body and there's no content length or content type. Okay. And notice that some of the characters are translated when they're encoded. So for example, Peter Lee, there was a space between Peter and Lee, and that got turned into a plus because URLs can't have spaces in them. And there's certain rules for translating characters that cannot appear in URLs when you're URL encoding them. Okay. All right. So HTTP has evolved for the past 30 years. In the early 90s, it was invented as just a document fetching service for the web at CERN, I think, for like documenting physics projects. And in those old days, web servers would just serve up static HTML files and image files, which is what you're going to do in Project 1. So you navigate to a URL, and that corresponds to a file that someone has written or uploaded on a server. And you get that back. So get index.html refers to file index.html that you can find in that server. Later on, like in the late 90s, let's say, web servers started to generate content dynamically. So it wasn't so much that you were fetching documents, but you're making requests. So the request would have a name like get product /123. If you're on an e-commerce site that has many different products, the URL might be specified, and the product name or number might be specified in the URL. And the server would look at that and then check a database to get information about this product 1234 and generate a page dynamically that shows like the image of the product reviews, and all that stuff, right? That's dynamic web. Later on, like around 2005, Web 2.0 came around, meaning that JavaScript became popular to allow pages to be interactive. So Gmail and Google Mail were really the first big Web 2.0 applications. And what I mean by that is that these were web pages that did not just like load once, but you loaded the page, and then as you did things on the page, more data would be fetched to change the page accordingly. Like as you moved around the map or scrolled to different messages in the application, the new data would be fetched, and the browser's image rendering would change without having to load a new page from scratch. It would be incrementally updated. And then the most recent kind of evolution in HTTP in this decade has been that HTTP is now used for many web applications, in particular for REST APIs, for client-server interactions of all types, like especially for like smartphone applications communicating with remote servers, and for servers communicating with servers, and all that kind of stuff. HTTP is often used, even though we're not dealing with web pages, but because it can be used as a generic request response mechanism. It's well understood and it's robust. You have all these libraries and software. You have caches and proxies. You have encryption and compression already built in. So the logic is, why not use HTTP for all your client-server request response interactions? And that's what's done. Okay. So here's an example of HTTP being used not for a web page, but for a REST API that provides weather information to clients. So here's a request that gets, sorry, this is bogus. There shouldn't be HTTP in there, in the URL line, I don't think. But anyway, so it gets a URL, which has some kind of API key, and then has the word forecast, because you're getting forecast information, and location equals San Francisco. So this is also user-provided information about that is like an input parameter to this request. And the response is 200 OK, and the content type application JSON indicates that the data provided back is a JSON object. So basically, someone's making a request for weather information for San Francisco, and here's all the weather information here that's in this response, right? And this is not used by a web browser, but by a software application that needs to rely on an outside service to fulfill its to operate. Yeah. And the HTTP works for this because HTTP provides places to specify input parameters like the URL. It allows you to specify data types, and the compression here is useful as well. And then the response, HTTP allows you to indicate success or failure and to provide arbitrary data back. So just to make it a little more concrete, here is a page documenting the Twitter API. Sorry, let me stop here. And so this API documentation shows a bunch of different types of requests we can make. Like you can post a new status update, which is to say tweet. You can read other tweets, which they call statuses, and you can retweet and so forth. And each one of those actions is mapped into a combination of an HTTP verb, post or get usually, and then a URL. And usually the name of the URL gives you some information about what it does. That's kind of like the method name in a library. And so, for example, if you're doing a retweet, then there are a lot of parameters you can provide that are documented here. But the response you get back is a JSON object. Here's an example. Anyway, I guess you have to read the documentation to understand what's going on, but many of you have sure run into stuff like this before. Okay. So when you're building an API on top of HTTP, like I said, you have inputs and outputs like any other functional interface, but where you provide those inputs and where you get the outputs is different. So one of your inputs is that you can choose the method, whether it's get or post or so on. You can specify URL. You can add query parameters after the URL, like key value pairs, or you can insert values in like sort of subdirectories of the URL. And you can provide an arbitrary body, which could be JSON data or pharma-coded data, whatever you want. And then the outputs you get back from the server are status code and a body, which is usually JSON encoded. And you also can include custom headers in the input and read headers in the output, but that's kind of frowned upon for API design. Usually it's best to let those headers be used for just like the HTTP layer rather than for your application layer. Which is a confusing term because HTTP itself is an application, but I mean the application that you're building on top of HTTP. Yeah. Okay. So I kind of already mentioned this, but why use HTTP for new applications? It's because you can leverage infrastructure that already exists. You have encryption, you have compression, you have basically every programming language out there has some kind of HTTP client libraries you can use. There are lots of robust servers like HTTPD, Tomcat, Node.js, Django, Flask, Nginx. Proxies like Squid are already available. And HTTP is generic enough to handle most applications you want to build. The only real disadvantages of HTTP are that you inherit some unneeded complexity, because HTTP might handle more than you're doing. And you also have these human readable headers, which on the one hand are nice because they make debugging easier, but they also make your messages longer. Although some of that is mitigated with compression, like gzip compression. And another weird thing about HTTP is the fact that your inputs are divided between the URL and the body of requests, and potentially a query string of the requests. So sometimes the inputs to your calls are placed in kind of arbitrary different parts of the request, which is kind of confusing. Yeah.
When you say compression, does that mean there are specific algorithms that only work with HTTP? Is that specifically because it's used so much more commonly than everything else?
What I'm saying is, I mean, the most common, the HTTP spec, I think, specifies that certain compression schemes are allowed. I don't really know if there's anything besides gzip, but I know that gzip is a very standard compression algorithm, and pretty much every HTTP server and client library allow that or support that, and that it's very fast and it's pretty good at compressing. So it takes, so most traffic on the web is like gzip compressed actually, and that's enabled by just adding this one line to your request that you accept encoding gzip encoding. Yeah, but I think that there's a limited number of acceptable, of commonly used encodings. I mean, there's nothing to stop you as a web browser from saying, accept encoding, migrate compressor. The problem is that if no one recognizes that string, no one will use it. You know, if you're designing your own client and web browser, and you're also designing your own web server, then you could design a new compression algorithm and use the same use a certain keyword for it, and implement it on both sides, and it could work great. Right? So it's an extensible protocol, but there are certain standards that you'll find are implemented on many different systems. Right? GZIP is basically the standard. Okay. The other application layer protocol we're going to talk about today is SMTP, Simple Mail Transport. And this is also built on top of TCP. And it's actually older than HTTP. This is like the first killer application of the internet in the 80s. And it uses port 25, okay, not port 80, but another low number port. There's a certain RFC that defines it, RFC 2821. And it's a peer-to-peer protocol used by mail servers to exchange users' messages. User agents, the actual people who are using email, have different programs that use different protocols to access mail, and will just send mail that uses the same SMTP protocol. But then among the mail servers, SMTP is used to exchange mail. So this is quite different than HTTP. It was invented a lot earlier. It's a lot simpler. This is what it looks like as an example. So the S and the C here are not part of the protocol. They're just indicating whether the client or server is talking. So in this case, a client is sending a short email message here. And the way it does that, it opens up a TCP connection on port 25, and the server responds by identifying itself, and then it says hello, and then it says, okay, great, glad to meet you, and then the client starts sending out, specifying different parts of the message, like who the message is from, who it's going to, and then it says it's ready to send data, and it sends the data, and then at this one, it ends with, the server actually tells here that you can end your data with carriage return line feed, dot carriage return line feed. So basically it's a new line that has just a period in it. And once the client sends that line, then the message is sent by the server, or is processed by the server. So I want to ask, how is this different than HTTP? Yeah.
Well, the client and server seem to be going back and forth rather than one request being sent and one response being received.
Yeah, a lot of like back and forth chatter, small messages. That's very different. This all could have been done with one request, right? One big request, like here's my message, here's who it's going to, send it please. And then the server would say, okay, fine, or sorry, I can't do it. That would have been the HTTP style of handling this, but that's not how this works. And specifically, the way I would put that is that it's stateful, meaning that the server has to remember what you previously said in order to fulfill your request. So on this connection, like the message is kind of gradually built up over several interactions. And by the time we get to here, the server has to remember not just this, but all these things that you said before in order to actually successfully send the message. Okay. With HTTP, that's not true. Every request can be handled independently. So you can actually try this out for yourself using Telnet to open up a TCP connection. And I'm going to give a little demo of that. Unfortunately, I wasn't able to switch to my Mac to get a terminal, but let's do that. And you can try this at home too, or like if you have your laptop, you can try it right now. So just give me a second to get ready. Because this is another sort of human readable protocol. It's not totally human readable, but it's text based. So both of those things make it such that you can just kind of type it out into a TCP connection think this will work. That's what I wanted. Mirror. Okay. Start. Alright. Okay, so here's my terminal. And so what I can do is use Telnet. Telnet is actually not installed on Macs. So you have a Mac, you can try to brew install it and that might work. But what I would do is just SSH into Murphy.
Yeah, brew works.
Does it? Yep. Okay, I don't want to do that. I tried that before class and it didn't work for some reason. Or maybe I would type it in. Let me try that. Telnet. So let's say I want to send an email to someone in class, okay, who has a .u.northwestern.edu address. First thing I need to do is figure out what the mail server is using NSLOOKUP. So you have to do a special type of DNS request. MX stands for mail exchanger. So u.northwestern.edu. Okay, so I make that request. We'll learn about DNS in the next lecture, but DNS is telling you these are some mail servers that can handle this domain. Okay, so so I can actually make a connection to one of these to send mail to that domain. So I'll use Telnet to create a TCP connection on port 25. Okay, yeah, that works fine. So my brew install did work. Okay, so I'm now connected to this server. The server sent me back this line, 222. It's giving me some information about the protocol version, I think, SMTP, extended SMTP maybe. And now it's my turn. So I say, what? Hello, u.northwestern.edu, and it responds at your service. I think, check the slides. Wrong class. So it's RCPT then 2 maybe? I think that's what I had on the slides before. So who wants to get a message? Yeah, what's your email address?
DGL.
Yeah.
At u.northwestern.
All right, great. I appreciate that because it's short. So that I messed up the syntax and it gave me a 503 error. See that? So I don't want to screw this up, so I'm going to quit and reconnect because it's stateful. I'm saying hello again. Can you guys see it even though it's on the bottom of the screen? Yeah. Okay, so this slide is actually first. You see RCPT2 : oh, I gotta say from first. Yeah, that was the problem. Yeah. So I disobeyed the protocol. I didn't tell it who the message was from. So from, and then just mail from. I gotta say mail from. 343 class. All right, I could actually put any email address in here if I wanted to, but I'm going to keep it legit, put my real email address. I think that was because I like hit the side character. You see all those garbage characters that appeared on the screen? When I erased them, I erased too many characters. Okay. So fortunately, this is not how email actually works. But in the old days, this is how people sent email. Like in the really early days, like when there's just a few people using email. Okay, hello, u.northwestern. Mail from, I'm just going to keep it simple, say Tarzia at northwestern.edu. Yeah. Mail from. We good?
Yeah.
Okay, so now it's time for planning. And then recipients to DGL. DGL.
Yeah.
Okay, that was accepted. Anyone else want to get one? Just anyone else have a short email address?
LITRE.
LITRE. Yeah. You guys are so lucky. All right. So that was accepted, and now I think I say data, right? Let's double check so I don't have to do this 3 or 4 times. Go ahead, it says. And now I actually have to type out the headers that will appear in the mail client. So I have to actually repeat the from and the to here in order to get the client to render it properly. I don't necessarily have to, but I have the option, the ability to. So I can say from class, and I'm not going to bother with a to, but I'm going to put a subject in here, tests from lecture, and I think that I need to put a carriage return, start at the body, like, hi there, I am writing this in a terminal. And then I'm going to put a period and enter, and then it said okay, I'm going to quit, and now check your email.
Yeah.
You got it? You got it. Excellent. Wasn't that amazing? Yeah.
Wait, so what happens if you specify a mail from
a different?
Yeah, just.
So like so email is not secure. You could put from Morty Shapiro or Morty what's his name? Shapiro, right? And that would be accepted and it would appear.
But so when you receive it, it would say Morty Shapiro.
Yeah.
Does it have to be a legit email address?
So it doesn't now. I mean, right, it could be. So there are so this is a very basic early version of email. Like later on, there are things built. There are different checks that are optional that are done to block spam and to make it more secure. And there are many different RFCs that do different specify different types of security and stuff. So for example, you can include in your DNS for your domain a public key that then has to be used by messages that are sent from anyone in your domain, and then the receiver, if they want to, they can check that your message has a header that's like a signature that actually matches the key that they find in DNS. So there are ways to make it more secure, but they're not universally implemented. So for example, Gmail accepted that message even though I didn't provide any authentication of who I was. Yeah.
So when you first started, you searched up which servers can handle Northwestern things. If you put it to any, you have to always search that for the emails you're sending it to, or?
Yeah. So the reason I did that was because if I want to send an email anonymously to someone, so if I connected to this is Gmail, right? You at Northwestern is Gmail. If I connected here and I tried to send an email to someone at Yahoo, the server would probably reject that message because it doesn't want to relay that. It's not responsible. It doesn't feel responsible to relay messages to outside users for unauthenticated users. It's willing to deliver messages to its own users from unauthenticated users because in general, email can come from anywhere in the world. It can't challenge everyone in the world who wants to send you an email with a password because it hasn't established a password with you. So yeah, I looked up the server for the addressee that I wanted to send to reach. Yeah.
So if you had done this exact same thing, but instead of using your email, you used my email, Gmail would just let that happen?
Yeah.
It would just be like, oh look.
It has no idea who I was. It doesn't know my laptop. It's my laptop and what my email address is.
So we could if we wanted to send emails to people and make it look like it was from someone else.
Yeah, so funny story about that. When I was in college, we had this game called Assassins, which was it was an icebreaker thing. But anyway, there were teams with squirt guns. If you sprayed you were assigned to assassinate some other team, 4-person teams. You had these little squirt guns. You had to squirt them in the back to get them, right? and you were given their photo of the people on the other team and their names, I think, or their code names or something. I think you were given their real names. But anyway, so the person who got me eventually, what they did was they sent me a spoofed email from the package center. So we had like one mail room where all our packages were delivered. This was before Amazon, so we weren't getting like 5 packages a day. But like, so if you got one of these emails, you'd be like, oh, someone sent me something. Let me go down and pick it up. It was like a big deal, right? So I went down to pick up my package, and there was no package, of course, just someone waiting to shoot me. Because they spoofed the message reliably, or like in a way that made it look authentic, doing something like this. Yeah.
So I know sometimes you can make HTML emails. Can you also like type out HTML body as?
Yeah. HTML email. I don't remember exactly what you have to do. I suspect that there's a certain header you have to include here. Like I said, I indicated the from, the subject. There's probably some kind of content encoding you have to specify. I think it's called MIME type. Anyway, you tell it it's an HTML message, and you type out valid HTML, and then that'll be accepted. I mean, as you try to get more sophisticated with what you're doing here in email, it gets harder to like just type it out and make it work, and therefore it makes sense to actually have a program that like goes from your intention to the code that goes out in the wire. Yeah, but it's possible. And you can use a program like Wireshark to trace the network traffic for your mail program. Like you could get Wireshark running, and if you're using like not webmail but like Thunderbird or like an actual mail program, then those programs use SMTP, although it might be encrypted, which would then defeat the packet sniffing. But you could potentially see inspect the packet, and like see what data is being sent, and then replicate it manually if you wanted to. Okay. So let me wrap up by, I think I just have one slide wrap up, doing a recap right now on my laptop. Okay, so we talked about application layer protocols. They're usually built on top of TCP, and in that case, you don't have to worry about the network itself. You just connect to some other host, and the operating system and the network, the routers, will handle the details of packets and ordering and all that stuff, which we'll talk about later. Most applications use a client-server architecture for requests and responses, but there are some peer-to-peer architectures that are more scalable but kind of difficult to organize. HTTP was invented for fetching documents from web servers, but nowadays it's used for many type of request-response transactions. And these include, HTTP includes URLs and the request method as part of the input, and the output is the response status and headers and body. REST APIs are built on top of HTTP. So we can think of HTTP as a layer in the networking stack in its own right, because they're actually things that are built on top of it. SMTP is an earlier application layer protocol, which is stateful, and you can use it to send an email, and it's also kind of human readable, but not totally. And again, just this distinction I'm making between stateful and stateless protocols. The stateful protocol requires the server remember what you previously said in order to operate, but in a stateless protocol. So HTTP is stateless, but cookies give it state, right? Cookies basically allow the client to know what it has to remind the server of the next time it makes the request in order for it to be recognized. The cookie is a reminder of who I am, basically. And the server can use that cookie to match up your current request to some previous request you got from you, basically. All right, that's it. And don't forget Project 1. Get started. It's going to take you a while.